Hi, in this video we are going to discuss another common technique for sorting values. It's called insertion sort. And basically, as the name says, insertion sorts will insert one value at a time into a sorted collection of values. So the idea is to maintain the collection of values sorted. If we're talking about an array, as we always do, the idea is to keep one section of the values in the array sorted and another section of the array with the unsorted values. And one by one, we're going to insert the values from the unsorted region into the sorted region. So the steps are very basic. First, we compare the first and the second values that we're given. We decide to swap or not if they are not in order. And then we grab the next value among the unsorted values and we insert it in order into the values that we have already sorted. Then we're going to repeat this process inserting one value at a time until all the values are sorted. So let's start with numbers that we have used in the past and let's try to sort them in increasing order. So as you can see, these are random values in random order. So according to the technique, the first thing that we're going to do is to compare the first two values, 29 and 10. Actually, what we're trying to do is to say 29 is the first value, is already sorted, because that is the only value that we have. So, in a sense, we're going to think about this as follows. There is a section of the array containing 29 which has the values already sorted, and there is another section of the array which contains the values which needs to be sorted. So what we're going to do is now try to insert 10 into the values that we have already sorted, which happens to be 29. Of course, 10 is less than 29. So now what we need to do is the following. We are going to leave 29 what it is, but then we're going to make a copy of 29 in the second element of our collection, the second element of the array. And now we're going to take the new value, which is 10, and we're going to insert it in the correct position, maintaining the collection that we have in sorted order. In other words, we're going to copy, 10 over 29. So right now, these are the numbers that we have sorted, and of course, there are some other numbers in the collection that we haven't sorted. And those numbers are 14, 37, and 13. Now we're going to repeat the process. In other words, this is the sorted collection, and this is the next number that we're going to try to insert into the sorted collection. And we realize that 14 has to go between 10 and 29. Okay? So we compare 10 and 14. 10 is smaller, so we leave 10 what it is. We compare 29 and 14. We realize 14 is smaller. We have found the place to insert 14. 14 should be the second value. But in order to do that, we're going to leave 29 what it is for the time being in the array, and we're going to make a copy of 29 in the third position. And then we're going to take the new number that needs to be inserted, 14, and we're going to copy it over 29. And this way, we have inserted 14 in order into the collection. We have two numbers which we haven't sorted, 37 and 13. And now we repeat the technique again. The task is to insert 37 in the correct place among these numbers. So the first step is to compare 37 and 10. 10 is smaller, therefore no need to change it. Compare 14 and 37. 14 is smaller, no need to change it. 29 and 37. 29 is smaller, no need to change it. Therefore, we simply insert 37 at the end. And again, we have four numbers which are already sorted, and we are left with only one number, which is 13. Notice that in this case, when we inserted 37, we did not copy any of the previous values, and that is because 37 is larger than the values that we have. So something to notice in this technique is sometimes we need to copy values to shift them as we call them, and some other times we don't. So let's try to insert the last number, 13. So we repeat the process. Compare that with every element among the sorted values until we find the place of insertion. Okay, so we compare 10 and 13. 10 is smaller, no changes. We compare 14 and 13, and we realize that 13 should be in front of 14. It's smaller. So now what do we need to do? Well, we'll leave 14 what it is for the time being, and then we copy 14, right? Then we copy 29 in this position, and we copy 37 in this position. So we shifted the position of every value by 1. Okay, 14, 14, 29, 29, 37, 37. Okay? And now what we're going to do is to take the value that we need to be inserted, 13, and put it on the right position, which is this one. And at this point, we're done. All the values are sorted. So basically, insertion sort works as the name says. We insert one value into the values that we have already sorted. Let's do some analysis. As you can see, in order to insert all the values, we have to repeat this technique n-1 times. n-1 because to insert one value, we don't need to do anything. One value is always sorted. To insert n, we need to perform this technique n-1 time. And as you saw in the case of inserting 13, there are some cases in which we have to shift values by one position, in this case 14, 29, and 37, as we did earlier, so we need to shift n-1 values. So the expected running time of this technique is big O n squared. Do not worry about the meaning of big O, this is just notation. What it means is that the time, the expected running time that applying this technique is going to take is quadratic, is n squared. Insertion sort is a quadratic sort. We have studied other sorts, or you should have studied other sorts, which are also quadratic, the exchange and bubble sort, and the selection sort. Now let's try to do something a little bit different with a different collection of numbers. So, for example, these numbers here, all right? So you will realize that these numbers are already sorted. So what happens when we apply insertion sort to a collection that is already sorted? Well, first step is always the same. The first value has to be correct, in the correct position. It's already sorted. That's 20. So now we try to insert 32. And to insert 32, we compare it to 20, and we say, okay, 20 is less than 32. No need to shift that value. There are no other values, so we simply insert 32 at the end. The next value is 45. And again, we compare that with 20 and 32. 45 is larger than those two, and therefore it should be attached at the end. 45. 49, when we compare that with the existing values, 49 is larger than those three, so it should be inserted at the end. 49. And finally, we realize that the same thing is going to happen to 61. In other words, the collection was already sorted, so there was no need to shift the values. No need to shift the values because they were already in the correct place with respect to each other. They were already sorted. This is a special case of this technique because copying didn't take place. So this is what we call the best scenario. Okay, that's the best that we can do in terms of running time. So the best scenario for the insertion sort happens to be only n, directly proportional to the size of our data. This is a big difference because the change or the differences between something being proportional to n and something being proportional to n squared is pretty big. Keep that on mind. So let's finish this video by analyzing a little bit of the insertion sort. So first, because we're inserting one value at a time, we are guaranteed that every time that we run this technique, a value will be in the correct position and the other values will be maintained in order. Second, every iteration may or may not shift more than one value. This is what is costly. This is proportional to the size of the data. And finally, the expected running time of this technique is n squared, but there is a best scenario case which is significantly different than n squared, and in this case is O(n). Keep this in mind when you analyze insertion sort.